Okay, thank you. I'm taking the algebraic perspective on quantum field theory, and there are a few formulations of algebraic quantum field theory, well, at least two, but they can be all expressed in terms of functors. So for my purposes, an algebraic quantum field theory is, in particular, a diagram of algebras. That is to say, a functor from some small category to category of algebras, where we probably want other structures on the algebras, such as topology, but I'm going to ignore that for now. And one of the main formulations, locally covariant quantum field theory, the category would be Locke, the category of spacetimes. But you could also have a category of regions in a fixed spacetime, for example. Anyway, so that's the reason why I'm interested in diagrams of algebras. So if you have a diagram of algebras, that is a functor that involves, well, a bunch of vector spaces, underlying vector spaces, and multiplication maps and morphisms. So if, for example, M, probably a spacetime, is an object in the category, then there's an algebra there, and that algebra has a multiplication map. So for big M, a spacetime or whatever, object in the category C, let little m hat denote the multiplication map in the algebra, and that's going to be a bilinear map like that. And there are three conditions that the structures of a diagram of algebras must satisfy. There's associativity, there's the fact that there's functoriality, and there's the fact that the maps that the functor gives should be homomorphisms. So let phi be some morphism in category C. That gives a homomorphism from the algebra. So phi is going from M to N. It gives a homomorphism from the algebra at M to the algebra at N. What does that mean? That means if you multiply things together and then apply the map, you get the same thing as if you apply the map and then multiply things together. So that can be expressed as this equation. And the thing to note about this is that the right-hand side is cubic, because you've got one m and two a's. So it's cubic in terms of the structures involved in the diagram of algebras. So cubic is a significant fact. Okay, let's see if... Okay, now think about deformations. First of all, about the classic story of deformations of an associative algebra, a single associative algebra. So you have the Hochschild complex of an algebra A. That has the structure of a differential graded Lie algebra, or I'll say DG from now on. So what is deformation? So F in degree 2 in that complex is a deformation of the algebra A if, when you add that to the multiplication map, you get an associative multiplication. But this is exactly the same thing as F satisfying the Maurer-Cartan equation. 0 is equal to the differential of F plus 1/2 the bracket of it with itself. So that's defined by the differential graded Lie algebra structure. And note that this is quadratic. And in general, I mean, this is the way that I've written it, this is exactly the same for any differential graded Lie algebra. So the differential graded Lie algebra gives a quadratic Maurer-Cartan equation. That means that is incapable of describing deformations of a diagram of algebras. You need something more to do that. So then, related fact, Conceivage formality, which is behind the classification of deformation quantizations, formal deformation quantizations, is based on L-infinity structures. The formality is expressed as an L-infinity quasi-isomorphism between two L-infinity algebras, but they're more special than that. The first is simply a graded Lie algebra of multi-vector fields on a manifold. and the other is the differential graded of the algebra of the Hochschild complex. But it's in the setting of L-infinity algebras. So to generalize Kontsevich formality or something like that, to apply it to understanding algebraic quantum field theory, what do we need? We need probably an L-infinity structure on the Hochschild bicomplex of a diagram of algebras. So differential graded Lie algebra won't do, but L-infinity could, because in an L-infinity algebra, you have a more general Maurer-Cartan equation, which can be potentially arbitrarily high degree, not just quadratic.
So what is the bicomplex now? Why bi?
Well, it's a complex, but it's very naturally expressed as a bicomplex. So the second degree is multilinearity, so that's the one that's familiar from the standard Hochschild complex. The first degree has to do with the category structure underlying it. So in general, a cochain here is, let's see, a PQ cochain is P multilinear, but it also depends on a chain of P composable morphisms in the category.
Okay.
So and there's the differential breaks down into two pieces, one of which looks familiar from Hochschild. The other involves basically composing morphisms. Any other question before I move on? Okay, so I'm going to talk about a few different operads. The first one is made of trees. It's called the brace operad. And what it's for is it describes natural operations on the Hochschild complex of vector space. That is to say, I take the Hochschild complex and ignore algebra structures or set that to 0 equivalently. So it's really just a graded vector space. So this has a basis which is labeled by planar rooted trees. So for the n-ary operations are labeled by planar rooted trees with vertices numbered 1 through n. And that order can be switched around. So here I have an example of how the partial composition works in this. So I've got 2 trees here. This 1, 2, 3, and this just with one edge, which I've colored red. The idea is, so we're composing at 1. So we're going to cut out the vertex 1 on the first tree, do a little bit of renumbering. So 2 is going to become 3, and 3 is going to become 4. That's a minor thing. But then we're going to look at all possible ways of reattaching the edges that went to 1 onto this tree that we're inserting. And then we just have the sum of all of those. It's all positive signs. It's actually quite simple. So here we've attached the edges just to vertex 1. Here, attached one of them to 1 and the other to 2. Here, attached them and the other. See, there's a planar rooted vertices, so the order of things matters. Here we attach them both to 2, etc. So this actually describes the brace operad. If you've seen the definition of a brace algebra, there's some confusing signs, but they actually come entirely from just applying the causal sign convention to the action of this. And the most familiar operation from this operad is the Gerstenhover bracket, which in this notation, well, first of all, the Gerstenhover bracket comes from the Gerstenhaber's composition operation, which is represented by this this tree with just 2 vertices. 1 goes to 2. And you subtract off reversing the order, so it's this tree minus this tree. That's it. There's also the actual, the eponymous brace operations, which generate this operad, are given by the corollas. So any tree that consists of one root and then just edges going directly to a bunch of leaves. Okay, with me. So a fancier operad is related to that is one made out of words. It has a number of names and notations and descriptions of it, but I think it first appeared in paper by Gerstenhover and Voronov, which is actually the same paper that introduced brace algebras. So this is a differential graded operad, and I'm denoting it as F2S for reasons I don't want to get into. This describes natural operations on the Hochschild complex of an algebra, so actually with the differential coming from the algebra multiplication. It has as a sub-operad the brace operad with a degree shift in it, which is where the signs start coming from. The basis for this is given by a set of words. So in arity n, these words, so word W, the letters of the word are the numbers 1 through n, and there are three conditions. One is that any of those numbers occurs at least once, so the length is at least n, and we never have letter repeated twice in a row, and you also never have any interlacing. You never have the word is something something A, something something B, something something A, something something B again. Those are the only conditions. This is graded. The degree of a word is the extra length. So it's the total length minus n. So that has to be at least 0 because all of the numbers 1 through n do occur. The differential. A
and B are just 1 to n, yes?
Yeah, they could be anything in 1 to n. Yeah. The differential is given by deleting letters, so the differential should have degree minus 1, so it should decrease the length by 1. And basically all the faces of a word are given by deleting letters from it, although you can't delete a letter that is to say a number, which only occurs once. And there's a somewhat long story about the signs, but here we have the word, this is word, 1, 2, 3, 2, 1. 3 only occurs once, but we can delete one occurrence of 1 or 2. So if you delete the first one, you get 2, 3, 2, 1. You delete the first 2, you get 1, 3, 2, 1. Delete the second 2, you get 1, 2, 3, 1, and you delete the last. Oh, sorry, that would be a mistake there. If you delete the last one, you get 1, 2, 3, 2. And there's also composition. Composition is related to the.
So you're not permitted to delete 3 because of interlacing, or because of this rule, second rule, or what?
Because of the first rule, because 3 has to occur at least once, so you can't delete the only 3.
Ah, okay. Also. Mm-hmm.
Composition, this is related to the composition with trees. I've got actually 1, 2, 3, 2 and 1, 2, 3, 2 again. I want to compose at 2. That means I'm going to kind of, aside from some renumbering, I'm going to cut out the 2 and replace it with the 1, 2, 3, 2, which is also renumbered by adding 1. The ways of putting it in are, see, 2 occurs in 2 places, so I have to split 1, 2, 3, 2 into 2 pieces and put those into those slots. But when I split it at a letter and I repeat the letter that I've split. And as I say, I'm adding 1 to some things. So if I cut it at 1, that becomes a 2. Get 1, 2, 5, 2, 3, 4, 3. If I cut it at the 2, well, see, you can cut it at any of these 4 places, which is why there are 4 terms in here. And there's a very complicated rule for the signs. Anyway, this gives us a differential graded operad. And it has other descriptions, such as being made of spineless cacti. Okay, any questions before I move on? Okay, now my first operad is the Quilt operad, which is made by combining these 2 things together. This is a differential graded operad. This describes the natural operations on the Hochschild bicomplex of a diagram of vector spaces. So basically the Hochschild complex that I'm interested in, except I set multiplication to 0, which makes things simpler. This is actually inside the Hadamard product of those 2 previous operads. So for the arity n operations, the space of those is just that is inside the tensor product of the arity n operations with the words and with the trees. And it's not the whole thing. The basis of it consists, in a nice way, of what I call quilts. And a quilt is a pair of a word and a tree, and they have compatibility conditions between the word and the tree. Remember that the arity is the same on both of them. So the vertices of the tree are the letters of the word, and those are in fact numbers 1 through n. So there's 2 compatibility conditions. If in the word u, which could be any of those numbers, occurs before v, then in the tree u is not below v. It's either above it or to the side of it. And in the word u, and then sometime after that a v, and then sometime after that another u, then v must be to the left of u in the tree. So these are my compatibility conditions, and that turns out to define a suboperad, a differential graded suboperad of the Hadamard product. So this is itself a differential graded operad. And there's a representation of this on the Hochschild bicomplex of a diagram of vector spaces. So that's a Quilt algebra. Okay. So my final operad is M-Quilt. So this is the one that's actually going to describe operations on the Hochschild bicomplex that I'm really interested in, that of a diagram of a diagram of algebras. So I had previously set multiplication to 0 for simplicity. Now I put multiplication back in kind of a formal way. So I have this operad is going to be generated by the Quilt operad and an extra generator, which I call M, for multiplication. So this has arity 0, so it's acting as if it's something in the algebra rather than in the operad. It has degree -1, and there are a bunch of relations that I'm not going to list. But they're based on how a multiplication would behave in the action of Quilt on Hochschild complex of a diagram of vector spaces. And the differential, there's the old differential from Quilt, and then there's an extra term involving M. It's basically bracketing with M. Yeah, so the idea is that there's an action of M-Quilt on the actual Hochschild bicomplex, and in that representation, M simply maps to the algebra multiplication, which in the Hochschild bicomplex is an element of degree 0, 2. So as I was saying, the first degree has to do with the length of chain. So multiplication is for every object of the category, so that's length 0. and it's bilinear, so it's the second degree is 2. So this is a differential graded algebra. It acts on that complex. A immediate consequence of that is the cohomology of that complex is the Hochschild cohomology, and that is an algebra of the homology of the operad. So Hochschild cohomology is a homology of M-Quilt algebra. So one of my objectives in this project was to understand if and how the Hochschild cohomology in this generalized setting was a Gerstenhaber algebra, and I was able to do this by explicitly constructing a homomorphism from Gerstenhaber operad to the homology, basically just mapping the generators to appropriate things and showing that they in M-Quilt and showing that they satisfy relations up to homotopy. So this S here is just a degree shift. Okay, any questions there? Then we get to L infinity.
Well,
So,
maybe some stupid question. What does it actually mean, a diagram of algebras?
So that was back on the first transparency. A diagram of algebras is a covariant functor from some small category to category of algebras.
So that's a definition of what?
That's the definition, yeah.
I see. Mm-hmm. Okay.
So L infinity, this is a classic differential graded operad. This one is simplest to describe in terms of its generators. And it has a generator for every arity. Well, it starts at 2. So for n greater than or equal to 2, it's got a generator Ln of arity n, which has degree n minus 2. And I want to construct a homomorphism from the operad L infinity to the operad Quilt to begin with. And being a homomorphism, it's going to respect arity and degree. So what could it possibly map Ln to? It's got to map Ln to something in Quilt that has arity n minus 2, and arity n and degree n minus 2. That actually turns out to be the maximum possible degree of an arity n element. And the formula for this is actually relatively simple. It's simply a sum with a sign, which is a long story, but it's you sum over all quilts with the correct arity and degree. So you're not picky, you just take all of them that could possibly make sense, and that gives you the right answer, fortunately. So that's a homomorphism, a DG operad homomorphism from L infinity to Quilt. How
did you define the degree in Quilt? There was this tree and this word, so how do you get the degree?
Yeah, so the degree, so the trees have degree 0 and the words have interesting degree, and the grading just comes from the word part. So in a quilt, the degree is the extra length of the word.
Ah, I see. Okay. Mm-hmm.
Yeah, so a homomorphism like this, I mean, the action of Quilt on the Hochschild bicomplex is a homomorphism to the endomorphisms of the complex. So you just compose those together, and you get a homomorphism from L infinity to endomorphisms of the complex, and that makes the Hochschild bicomplex for a diagram of vector spaces into an L infinity algebra. So then we move on to M-Quilt. well, so the M in Quilt is kind of acting like a virtual element of the space that it's acting on. It's formally a multiplication. It's because of the relations that I didn't list but used to define Quilt. It automatically satisfies the Maurer-Cartan equation, sort of within the operad in a sense. And that means that it can be used to modify a map from L infinity into the operad, or rather into the new operad. So what I get is, so I called the first morphism K. This morphism is J from L infinity to Quilt. And the formula is pretty simple in terms of the previous one. So J of Ln is just K of Ln plus K of Ln plus 1 composed with M. And in principle, this is a simpler special case of more general thing where this would be basically an exponential series. You would have more and more m's composed and dividing by factorials. But the higher terms are all 0 in this case, so it simply has these two terms. So that gives me what we want, which is a homomorphism from L infinity to Quilt, and Quilt is acting on the Hochschild bicomplex of a diagram of algebras. Okay, any question about that slide? So that brings us to Maurer-Cartan equation. So this homomorphism makes our bicomplex into an L infinity algebra. And that means that we have a Maurer-Cartan equation defined there. Now, say a little bit more about this complex. Inside there, it's useful to talk about the asimplicial subcomplex, which consists of the part where the second degree is at least 1. So see PQ, P can be anything, Q has to be at least 1. The reason this is interesting is because the pieces of a diagram of algebras, the two things that can change, are the multiplication, which comes out as something in degree 0, 2, and the morphisms, the morphism part of it, which comes out in degree 1, 1. So there's no degree 2, 0 part in that. Anyway, this is a subcomplex, and it's an Quilt subalgebra, so we get immediately from that this is an L infinity subalgebra, and the Maurer-Cartan equation is defined on that subcomplex. So on that subcomplex, most of the terms of the Maurer-Cartan equation, which has infinitely many terms in principle, most of them are 0, but it actually stops at the cubic term. So the Maurer-Cartan equation in the asimplicial subcomplex is only cubic. Just like something we saw before, the solutions to that Maurer-Cartan equation are precisely the deformations of the diagram of algebras, as a diagram of algebras. So the Maurer-Cartan element, which, well, in terms of the total degree, in terms of shifted total degree, it has degree 1. In terms of total degree, it has degree 2. So that in this subcomplex has components of degree 0, 2, and 1, 1. So you take those things for a solution of the Maurer-Cartan equation, and you add them to the multiplication and to the morphism part of the functor, and you get another diagram of algebras. But something else you can do is to consider the Maurer-Cartan equation for the full complex, where you also have a degree 2, 0 piece. That Maurer-Cartan equation goes a little bit further, but stops at the degree 4 term. So it is a quartic Maurer-Cartan equation. the solutions of that are precisely deformations of A to a skew diagram of algebras, which is something I defined a few years ago. So what's the difference between that and a simple diagram of algebras? The difference is that you get something at degree 2, 0. So what's something at degree 2, 0? Given it's a gadget when you put into it a composable chain of two morphisms in our base category, it spits out an algebra element. So what you get is this is a bit like a diagram of algebras, except there is a failure of functoriality. So it doesn't totally respect compositions, but its failure to respect compositions is controlled by this this thing that depends on a chain of two morphisms. So yeah, if you have two morphisms, it doesn't A does not respect the composition of those two, but its failure is given by conjugating by an element which is given, is specified. So that's how these things fit together. And I have, oh, that worked. I have a couple of papers talking about this stuff. So the first paper, a few years ago now, a couple of years ago now, is a cohomological perspective on algebraic quantum field theory. This is where I talked about skew diagrams of algebras originally, and about the relevance of the Hochschild bicomplex to algebraic quantum field theory. And then I have a much more recent paper in which constructed these operads and their actions on the bicomplex and these morphisms, and I checked a lot of signs, but they all worked in the end. So that's the more recent paper, Operations on the Hochschild bicomplex of a Diagram of Algebras. So that's my presentation, and I've got time for questions. And I've got a whiteboard behind me for answering questions.
Okay,
So,
thank you very much. So are there any here in the seminar room? Maybe let me ask, so this is a very abstract approach you have. Is there
Yes.
Is there any kind of example which related to normal type of quantum field theories with fields and some spaces and then quantized, even if a free theory, but you in particular you spoke about deformations. So what would this be?
Well, I haven't worked anything through yet applying the newer stuff. In this first paper, I did go about, let's see. So if you have an infinitesimal deformation, then that is going to be characterized by a Hochschild cocycle. So I looked at, for like a scalar field theory, how do you construct, so I looked at a scalar field theory and imagine a term that you add to the Lagrangian, parameterized, well, sorry, multiplied by lambda, and then you look at how the theory changes to order 1 in lambda.
So an interaction which you add?
So an interaction, yes.
And what was a free theory, like just quadratic Lagrangian first, or what?
I was starting from, from I think a free scalar field theory. So that's one thing. The thing about this Hochschild cohomology is there are two ways of there are two basic ways you might want to deform a field theory. One is by adding an interaction to a theory. The other is by quantizing it. So these are, in some sense, the same kind of thing, and Hochschild cohomology treats them on the same footing. They just, an interaction is a part in degree 1, and quantization is something in degree 0, 2.
I see. And is there also some renormalization? Is it somehow visible in your approach, or this is assumed to be already regularized, or what?
This is assuming that things work. This is, yeah, kind of looking at the structure of things rather than the details of actually constructing them. But hopefully this will mesh together with actually constructing things and produce something useful.
I see. Any other questions from here, or otherwise online? Just unmute yourself and ask.
I have a quick question. In your approach, you kind of don't restrict your deformations to preserve the commutativity of space-like separated observables. So did you think about looking at the combination of Hochschild and Harrison cohomology to kind of encode that Einstein causality property?
Yes. Well, I thought about thinking about that. So this produces a further level of complication, obviously.
Yeah.
So it's something I'm kind of intending to get back to, but it turned out that working out all of the details and signs for this was complicated enough. So I've done this first, and maybe I can come back to that. When I first thought about it, so the Hochschild cohomology is given by a bicomplex for a diagram of algebras, and it was kind of looking like I needed a tricomplex to deal with space-like commutativity, which was more than I could picture at the time. But yes, it would be interesting to put that in. There's some indications that that space-like commutativity in practice tends to kind of take care of itself if you're starting with something that satisfies it. But obviously, I would like to understand it more precisely than that.
Yeah, that would be very nice. Thanks.
Okay, any other questions?
I have a question, just quickly. So when your category is the arrow category, and well, it's just when you diagram, it's just a pair of algebras and the morphism between them, homomorphism between them. So do you recover the result? Well, the L infinity algebra constructed by Martin Markle, and the name of the collaborators escapes me at the moment. Some years back.
So let's see. I found out about that paper after I put this one out, and this is something I need to put some more work into understanding. And certainly, my expectation that the L infinity algebra is exactly the same. But it's presented in a very different way, so making the connection is a bit difficult. But I think they both serve the same purpose of getting the correct Maurer-Cartan equation. So certainly expect that they're the same.
Okay.
In the BV language, one also can consider deformations of field theories. in the corresponding homologies. Is it related in some way to what you do?
Probably. Yeah, so, I mean, in BV, let's see, BV can work together with locality, but it's not absolutely intrinsic to it. Whereas in what I'm doing here, locality is absolutely fundamental. So it's not exactly the same thing, but they certainly should work together, but I don't yet know how.